All right, so ladies and gentlemen, this second half is just talking about these two practice problems for finding center of mass, which is we're going to find is quite useful when we're talking about rotation, because knowing where the center of mass is kind of also is important for making sure we don't have things rotate when we're trying to balance them. Okay, basically it goes back to a seesaw. You want to make sure you have the fulcrum in the right spot when you're trying to rotate something. So with that being said, our first example problem is this weird little setup right here. So I have a sphere, and it's got a mass of 1 kilogram and a radius of 5 centimeters, and it's welded to the end of a thin rod. All right. Now the rod right there, it says it's just rod AB, and what's important about it is a length of 50 centimeters, and it's got a mass of 0.5 kilograms. Okay. Now I'm trying to balance it on a knife edge because I'm going to look really cool in class trying to do this, and I'd like to figure out where should I put that knife edge so that everything will be balanced. Okay. And from what we've talked about, we know that the balance point is just a fancy way of saying the center of mass. So we really need to calculate the center of mass of this system. Okay? So the first thing we do is we ask ourselves how many objects are in the system. All right? And in this case, there's only 2 objects. There's that metal rod and there's the sphere. All right? So there's just 2 objects. Now, what we have to do is we have to kind of treat them like they're just little point objects, all right? Which means we need to figure out where the center of mass of the rod is and the center of mass of the sphere, okay? So to do that, first we just think about how long is this object in general, all right? And looking at it from point A all the way to the end of the sphere, we can tell that the rod says it's 50 centimeters, and then it says that the radius of the sphere is 5 centimeters, okay? Well, that means that if the radius is 5 centimeters, the diameter has to be 10 centimeters. So that means that going all the way across, if I start all the way on the left side and go to the right, I start 50 centimeters, then I go 5 centimeters, then I go 5 more centimeters, which means that the total distance is 60 centimeters. All right, and why that matters is because we want to figure out where the center of mass of these objects are so that we can kind of calculate the total center of mass. Okay? Now, let's start with the rod. Just like the meter stick, we can pretty much assume that if this rod is uniform, the center of mass is going to be right in the middle. And usually for any sort of uniform object, the center of mass is always going to be in the center. So in this case, if it's halfway down the rod, that means the center of mass position here is going to be at 25 centimeters. Okay? So, using kind of setting up our little formula, XCM is going to equal first the mass of the rod, which the mass of the rod looking at it is 0.5, times the position of the center of mass, which is going to be 25 centimeters or 0.25 meters, plus the position of the center of mass of the sphere. Okay. Now, as we talked about, because it's a uniform sphere, we can just assume the center of mass is right smack dab in the middle, which means if we look at where it is in its position, if I'm going from left to right, remember, the rod is 50 centimeters long. I go another 5 to get to the center of the sphere. So the position of the center of mass of this sphere is at 55 centimeters. Okay? So that means the mass, to find it, you do the mass of the sphere, which is 1 kilogram, times its center of mass position, 0.55 meters. All right? And right there, now we have pretty much everything we need to solve this. So we do that, then we do divided by the total mass of the system, which in this case is 1.5 kilograms. And if you do that calculation and go through, you should get that the knife edge needs to be placed at approximately 45 centimeters in order to balance this whole system. Okay, so the reason we do stuff like this, the reason we simplified this before we find the center of mass, is because objects like a rod or a sphere are annoying. All right, and it's much more annoying. Let's say I picked a rather weird looking shape and you knew where its balance point was. It's much simpler to reimagine that weird looking shape as just a point where all the mass acts when you try to calculate the center of mass. All right, so right there, that's our first practice problem for this. The second practice problem for this has to do with a little bit more complicated situation. All right. Now, of course, things don't always just act in one dimension. Sometimes they're in two or even three. But really, all you do is the same setup as before. All right. You just have to calculate the center of mass twice. And what you have to do is you have to find first the position of the center of mass for the x coordinate, and then you do the position of the center of mass for the y coordinate in this particular setup. All right. So what I mean by that is the following. So we want to find the center of mass of this whole system, this little triangle. Each object has a mass of 1 kilogram. We'll notice that this is now in 2 dimensions, so we're going to have to find basically a xy coordinate. So let's start by finding the position of the x center of mass. And I know this is very confusing because I'm using a capital X to represent this position. So, looking at these 3 objects, there's 3 objects in our system. So we start by looking at where the x position of the first one, M1, is. All right, this is a 1 kilogram object, but looking at it, its starting position is at 0. So we're going to say times 0. All right. Next, we add the position of the next one. It's now at a position of x equals 1. This is 1 kilogram times 1, and it doesn't give units, but we're going to assume this is in meters. And then for the third and final position, we're going to do 1 kilogram times where that M3 is, which in this case is at a position of 2 meters. All right. Now, once we do that, we just divide it by the total mass of the system, because that's how we use the center of mass formula. So in this case, the total mass of the system is 3 kilograms. Oh, no. I'm not starting a new line. So, with that being said, we'll notice that the x center of mass position, if we calculate that, is at approximately 1 meter. Okay? And honestly, if we look at it, that kind of makes sense, because looking at the 3 pieces, so we'll rewrite it real quick. The position of the center of mass of the x is going to be 1 meter. And if we look at it, that makes sense, because if we look at the x positions of these 3 things, they're all 1 meter apart. So if we kind of just ignore the fact this is above the other ones, it would make sense that the center of mass in the x plane is going to be right in the middle of these 3 things. All right? So we found the first position, the first coordinate, but now we want to find the position for the second one. All right? Now to do that, we're going to have to do this calculation again, but this time we're doing it for the y positions. All right? So just like we did before, and I'm going to just copy this just to make it a little bit easier. We're going to do the y positions of the 3 objects. Now, M1, looking at it again, M1 has a y position of 0, so this is going to be 1 kilogram times 0. M2 has a y position of 1 meter, okay? But M3, once again, has a y position of 0, so we're going to have to multiply that again by 0. Then, of course, the total mass of the system is still 3 kilograms, so we divide by the total mass. And when we do that, we're going to see that the the center of mass position on the y plane is going to be equal to actually less than 1 meter. It's going to be 1/3 of a meter. Okay? Which means that the center mass is probably sitting right about here. And honestly, if we look at it, that makes sense and kind of relates back to what we saw in our lab. Because when we kind of did this balancing point, the balancing point liked to hide closer to where the multiple masses were. All right? And when we talk about torque, we're going to see exactly why that is, because it has to do with the idea that torque has to stay balanced. Okay? So the center of mass of this triangle is going to be at 1 meter. I guess the coordinate would be 1 meter, 1/3 of a meter. All right? But right there, ladies and gentlemen, we just want to see the idea that the center of mass is just a situation where we're just looking for where something's kind of all its mass is concentrated and where you can balance it. All right? And lots of things have center of mass questions. Momentum does a lot of stuff with center of mass when things are kind of having collisions. But with that being said, ladies and gentlemen, that's where we're going to stop for today with this particular discussion. If you have any questions, shoot me an email. Otherwise, I'll talk to you later.